Hello and welcome back to Conquering Algebra 2. This is lesson 29. In this lesson, we're only going to be talking about one concept, and that is more on the uniform motion problems. In our previous lesson about uniform motion, we had two cases that both had the same distance. In this lesson, we're going to have a continuation talking about a total distance, and it's really going to be a situation of distance 1 plus distance 2 equals k, our total distance. And so different ways that our map could look is we have one person that is starting out walking and then they end up hopping on a bike and the rest of the way. So we have two different rates, the rate of walking and then the rate of the bike. Another situation is where we have two cases and they start in the same place, but they go in opposite directions. So leaving a train station, one train is northbound, the other train is southbound. How long until they are X amount of kilometers apart or something like that. And then the other one is where they are starting in different locations and they are meeting up in the same spot. So these are the three diagrams that we're going to be working with. So let's get some practice in. Okay, so in the first example, we're talking about Napoleon and he's trying to get back to the battlefield. He's going to walk for part of it and then he's going to end up riding on a caisson. He walks at a rate of 3 miles per hour. He rides at a rate of 9. The total time was 8. And we also know the whole distance to the battlefield is going to be 60 miles. So all of that is information that I want to use. So 60 miles is the total distance. He's going to walk and he's going to ride. So we have 3 for walking and ride is at 9. And then the total time is 8 hours. And then the most important thing, how long did he walk? That's asking for time of walking. So setting this up as a diagram for us to visualize what this is going to look like, he is going to start out somewhere. He's going to walk, and then he's going to switch to ride. This whole thing, which is rate of walking, time of walking, plus the rate of the ride, time of the ride, this whole thing will equal 60 because however long it took him to walk and however long it took him to ride, those two combined are going to be 60 miles. So that's going to be our master equation, our key equation as your book calls it. So we have the rate of walking, time of walking, plus the rate of the ride, time of the ride equals 60. And if you're not sure where we got R and T, remember that distance equals rate times time. So instead of saying the distance that he walked and the distance that he rode, I changed those to rate and time because that's what all of our little equations are going to be about. Okay, so it says that he walked at 3 miles per hour and he rode at 9. And then it says the total time was 8 hours. So that's going to be the time of walking plus the time of the ride equals 8. Okay, so now I have 1, 2, 3, 4 equations and I have 4 variables. So now we have the right number of equations. We can start plugging this information in here. One thing that I noticed is that with this 4th equation, there is no variable that's isolated, so I'm going to have to make that happen. And just a little tip, the question is asking how long did he walk? So if I'm trying to solve for TW, I want to leave my TWs in here. So I am going to solve for TR. That way I can replace it in here with TW, and that way whatever answer I find, that's going to be my answer for this question. So we can plug this in now. Okay, so instead of RW, we're going to say 3. We're going to leave TW as it is because that's the thing that we're wanting to find. Plus, R of R is 9 and T of R is going to be 8 minus TW equals 60. So now we're just going to solve for TW and be done. Okay, so 3TW plus, this is going to be 72 minus 9TW equals 60. So we're going to subtract 72. And we're also going to add our like terms. So this will be negative 6 TW because we have negative 9 plus 3 equals, and then this will be negative 12. Divide both sides by negative 6. And TW equals 2 hours. And so there we go. Now we know how long he walked, and I could see why he would want to upgrade to a caisson, because 60 miles at 3 miles per hour, that would take him a long time to get to the battlefield. The battle would probably be over by the time he got there. So there we go, and we're done. All right, so in our next example, we have Edward Longshanks and Queen Eleanor. So we're in England right now. They were 54 miles apart at dawn. Edward's gonna start journeying out to meet up at 8 a.m. at a rate of 3 miles per hour. 2 hours later, Queen Eleanor is gonna start heading that way also. They're gonna meet up at 4 p.m. and the question is, how fast did the Queen travel? So we want to know R of Q. So just doing a diagram to visualize, they're starting out at different places and they are going to meet in the middle. So we have the rate of Edward, time of Edward, and then the rate of the Queen, time of the Queen. And when I add those two together, I should get 54 miles. Okay, so now looking at other equations that we can plug in here, we know that the rate of Edward is 3. And then we know the time of Edward, because he started at 8 and they meet up at 4. So that is a total of 8 hours. And then we also know the time of the Queen. She starts 2 hours later than Edward. So her time is going to be 6 hours because she's going to be 2 hours faster than him. So cool, that's good. All right, so now we need to write this out as our key equation and then plug this stuff in and solve for the rate of the Queen. So we have R of E, T of E, plus R of Q, T of Q equals 54. And I'm gonna change colors now. Okay, so instead of R of E, we're gonna say 3. The time of Edward was 8. Plus, the rate of the Queen is what we are trying to solve for. The time of the Queen was 6, and the total distance was 54. So now we're just gonna multiply and solve. So 24 plus 6RQ equals 54, and we are going to subtract 24. So 6R of Q equals 30, divide by 6. So the rate of the Queen is 5, but not just 5 miles per hour. With these questions, we have to remember to include our unit of measurement. So in this case, we're dealing with a rate, so it's gonna be miles per hour. All right, and in our last example, we have at noon, Rocket Man whizzed off toward Rocket Land. 1 hour later, Moonfa whizzed off in the opposite direction. So she's leaving, Moonfa is leaving from the same place, whizzed off in the opposite direction at a speed of 200 kilometers per hour, less than Rocket Man. If they were 11,800 kilometers apart by 5 p.m., how fast did each travel? So that means they want me to find the rate of Rocket Man and Moonfa. So they're starting in the same place and they're going in opposite directions. So on my diagram, it's gonna look a little something like this, because they're starting in the same place and going in opposite directions. So we have the rate of Rocket Man, time of Rocket Man, plus the rate of Moonfa, time of Moonfa is going to equal, and it says that they are 11,800 kilometers apart. So there's my key equation. We know that Rocket Man left at noon and we're stopping at 5. So the time of Rocket Man is going to be 5 hours. And we know that Moonfa left 1 hour later, so Moonfa's time is going to be 4. We still need one more equation, and it needs to be something about rates because we haven't done anything about that yet. We do notice that that Moonfa travels 200 kilometers per hour slower than Rocket Man. So when we're talking about the rate of Moonfa, it is the rate of Rocket Man minus 200. Okay, so now I have 4 variables and I have 4 equations, so I can start plugging this stuff in. We have the rate of Rocket Man, time of Rocket Man, plus the rate of Moonfa, time of Moonfa equals 11,800. And because all 3 of these equations have a variable isolated, we're good to go. So let's start plugging in. So we don't know the rate of rocket man. We're gonna have to leave that as is. That's gonna be what we're solving for. And T of R is 5 plus, and then for rate of Moonfa, we have R of R minus 200, and then Tm is 4 equals 11,800. Just enough space. So from here, we just solve for R of R. So 5 rate of rocket man plus 4 rate of rocket man, because remember this 4 gets distributed, even though it's listed in the back, it's still gonna get distributed to both parts. Minus 800 equals 11,800. We're gonna add 800 to both sides. So that's gone, and we get 9 rate of rocket man equals 12,600, and we're gonna divide by 9. And our rate is going to be 1,400, and then we can't forget our unit of measurement, kilometers per hour. So the rate of rocket man is 1,400 kph, and that means that the rate of Moonfa is 200 less than, so it's going to be 1,200 kph. All right, and so we found both rates, which is what they wanted, so we're done. Okay, and that's it for lesson 29, dealing with uniform motion whenever we're using both distances to get a large distance traveled. Either they're both going in the same direction, they're going in opposite directions, or they're both meeting up. All those different variations. I hope this was really helpful for you guys. Be sure to subscribe so you get updates as we post anything new. If this was helpful, give it a thumbs up. If you have any questions, be sure to leave them in the comments below, and I'd love to help out. And for my Algebra 2 students, I'll see you in class.